students, in the next example, we can see that we have a ferromagnetic core, and the depth of the core into this screen is 5 centimeters. So we can say the core is actually like this, and this depth is 5 centimeter. Find the value of the current. We have to calculate this current that will produce a flux that will be moving through the core. Now we should remember same flux will be moving through the core that will be being produced by the source, and we have given the turns also, and we require a flux of 0.05 Weber. What is the flux density at the top of the core? What is the flux density at the right side? So this is the top of the core, top, and at the right side, assume that relative permeability mu r is given. So students, we know that the flux will be same at the top also and on the right side also, but the flux density will change because we can see the cross-sectional area of this part is different than cross-sectional area of this part. So the first approach will be we have to calculate the flux. If we know the total flux, then we can calculate the flux density in the top, that is flux total divided by area of the top, and on the right side it will be same the flux total at the area at the right side. Now to calculate the total flux, we have they have given us, find the value current, they have given us the flux, they have given us the total flux, but what they are asking for is the current. We have to calculate the current. So if we know the total flux, that is already given, and if we know the total reluctance that we calculate, then from this equation we can easily calculate I, and once we know the I, we can solve our first part, and the second part will be solved like this. So let's first make the equivalent magnetic circuit, and the equivalent magnetic circuit is, we want to calculate RT, so we can calculate I. So the equivalent magnetic circuit will be, we have how many reluctances here? One reluctance of the core will be from this area to this area, and I will call it R1. Okay, so the reluctances in the core, we can see that we have the left side, then we have this side also, and then we have this side. And then we have this side, and we have this side, and they are actually will be the same value of these two reluctances. So if I will call this as R2, if I call this reluctance as R2 and this reluctance as R3, and these two reluctances, as they are same, I will call them R1 with the combined. So let's first calculate R2 and R3, and then we'll see what is R1. So for R2, we can see that it is actually equals to L2 divided by mu area of the left side, A2. So what will this become? What will be the area of this side? We know this is, let's first calculate the mean path length. So from here to here it is 15 centimeter, and from here to this side is 7.5, and similarly from here to here it is 7.5 centimeter. So the length of L2 will be 30 centimeter, that is 0.3 meters. Mu is mu naught into mu r. Mu r is 1000, mu naught we know. And about the area A2, the depth that is into the core, that is 5 centimeter, and the width of this side, the left side, the width of the left side is 10 centimeter. So the area will be 10 into 5 equals to 50 centimeter square, or equals to 50 into 10 raised to power minus 4. So the value of R2, that is the left side of the core, will be then R2 equals to, if we put all these values, 47.75 kilo ampere turns per Weber. Now let's look at R3. And R3 is this side, this is R3. Again the length is same. Let's first write the formula for R3. R3 equals to L3. Where is L3? This is L3 over mu into A3. A3 is the actually area of the right side of the core. And the values for this, we can see for L3 again the length is 30 centimeter equals to 0.3 meter. How? From here to here it is 15. From here to this area is 7.5, and again 7.5, 7.5. What about the area of cross section? Let's see. The width of this is 5 centimeter, and into the core it is also 5 centimeter. So the area of cross section for this side will be 5 into 5, that is 25 centimeter square, or you can write 25 into 10 raised to power minus 4 meter squares. And by solving this, the value of R3 will become 95.49 kilo ampere turns per Weber. So we can see that it is narrower than the left side. That is why we have higher reluctance. Now let's look at reluctance 1. And reluctance 1, I am actually combining the top of the core and the bottom of the core. So if you look at this, this is getting a little messy. So from the top of the core, the distance is actually 27.5, and here we can see 5, then 20, then 2.5 up to here, 27.5, and if I combine the bottom part also, it is 27.5. So this will become 55 centimeter. So R1, that is combined, is the top and bottom length, mu and area of top bottom. So this will actually become 55 centimeter. I am writing them together, that is equals to 0.55 meters. Mu we know. Top bottom area, let's look at the width of that side. It is the width of the top side is, we can see 15, and the depth is 5. So 15 into 5, we will have our 75 centimeters square equals to 75 of 4 meters square. So we can say that R1, the value of R1 will be, that is the two parts combined, will be 58.36 kilo ampere turns per Weber. So this was actually our magnetic circuit. Here R1, R2, R3 we have calculated. R1 is the combined resistance of top and bottom. So the total reluctance that will be calculated, we will add R1, R2 and R3. And the value of total reluctance will then come to be 201.6 kilo ampere turns per Weber. This is the total reluctance. And as I told you, the first part was we have to calculate the current. So to calculating the current, let's see how can we calculate the current. We know that F equals to omega t RT. This we have calculated, this they have given, and F equals to Ni. So I equals to RT divided by N. So the value of the current (2.52 amperes). Yes. So this will be the current which will be producing flux T. They have given us 0.005 Webers. Now the next part was to calculate the flux density at the top of the core. So flux density at top of the core can be calculated as the total flux. They have already given to us. What is the value of the total flux? 0.005 Webers divided by area of the top or bottom. So what is the area of the top? Is 15 into 5, that is 75 into 10 raised to power minus 4 meters square. And this will become 0.67 Tesla. So on the right side, if the flux remains same throughout the core, and area of the right side we have seen, and this narrow side we have also calculated here, where there was R3. This was the area for the right side. This is 5 centimeter wide and 5 centimeter in depth. So this was 25 into 10 raised to power minus 4 meters square, and this is same. So this will become 2 Tesla. So this is how we have solved this equation. I hope it helps.